The paper I will introduce is Baseball, the rational pastime. This paper introduces the baseball algorithm, which provides a simpler and more efficient way to identify conditional irrelevance and requisite information compared to existing methods. Key insights in the paper are as follows. First, belief networks and influence diagrams can efficiently capture and represent a significant amount of knowledge in their graphical structure. Second, statements of conditional irrelevance or independence in belief networks can be verified in time linear to the size of the graph. And third, the identification of requisite information or the information needed to compute a particular inference query or decision problem can also be determined in linear time. For belief networks, the Bayes-Ball algorithm runs in time linear to the size of the active part of the graph, which is significantly faster when most of the graphical knowledge base is irrelevant. For decision problems represented by influence diagrams, the Bayes-Ball algorithm provides an even greater improvement, running in time linear to the size of the graph, whereas the previous fastest algorithm had a runtime proportional to the number of decisions times the graph size. This section, Notation and Framework, lays the groundwork for the Bayes-Ball algorithm by defining concepts related to the irrelevance and requisite sets. Starting from a belief network B equals NAF with nodes N arcs A and a subset F containing nodes that are functionally determined by their parent nodes. A joint probability distribution for the network is given for every node, expressed in either probabilistic or deterministic terms. The definition of probabilistic irrelevance is given below, which suggests that given the observation of xk, observing xl leads to no contribution to the knowledge of xj. Two propositions are given on irrelevance. Proposition 1 specifies probabilistic irrelevance for subsets through the irrelevance of all individual nodes across these sets. The second proposition specifies deterministic irrelevance. It defines a deterministic node as a node whose value is certain or effectively observed when the parents of the node are observed. It introduces the notion of functional determination, where a node is said to be functionally determined by a set of variables if either the node itself is in the set or its value is deterministic function of the variables in the set. Proposition 2 formally defines that xj is functionally determined by xk if xj is irrelevant to the entire network when xk is given. The section on target sets defines important sets in belief networks and influence diagrams that need efficient computation. The following discussion assumes the objective of computing the probability of xj given xk. The first set is the irrelevant nodes for xj given xk. It is represented as xnij given k, which refers to nodes that are conditionally irrelevant to xj given xk. Next are the requisite sets. The paper highlights that the requisite information required to compute the probability of xj given xk depends on probabilistic irrelevance rather than the conditional irrelevance revealed in the belief network graph, and that the graph only allows for recognition of the information that might be needed for any probability distribution. Two types of requisite sets are introduced. First, the requisite probability nodes set. It contains nodes where conditional probability distributions and possible states might be needed to compute the probability of xj given xk. For a deterministic node, the conditional probability distribution is usually a deterministic function. Next is the requisite observation set. It contains observed nodes for which observations and the possible states that might be observed could be required to compute the probability of xj given xk. The concept of d-separation is important for the Bayes-Ball algorithm since it defines the concept of active path, which is later traversed by the algorithm. An active path from a set of nodes j to a set of nodes L given a set of nodes k is defined as a simple trail or undirected path between nodes in L and in J. On such a path, every node with two incoming arcs on the trail is either in K or has a descendant in K, and every other node on the trail is not functionally determined by K. K is said to deseparate J from L in a belief network if there is no active path from J to L given K. And this non-existence of active path determines all irrelevancies represented in the belief network. The paper then introduces the Bayes-Ball algorithm, which has two versions, a simpler preliminary version and a more refined final version. The simpler version sends a bouncing ball to visit nodes in the belief network, starting from nodes in J, and the ball can either pass through, bounce back, or be blocked depending on the type of node and the direction from which the ball came to visit. The summarized rules are illustrated here. First, an unobserved node can pass balls through to children or parent, and can also bounce back balls from children. Next, an observed node bounces back balls from parent, but blocks balls from children. Finally, a deterministic unobserved node always passes balls through. An example is shown here for the simpler Bayes-Ball algorithm. In this belief network, J contains only 6, and K contains 2 and 5, denoted by the shading. Starting from the rounded rectangle beside 6, node 6 is first visited. Then, from node 6, the ball is passed through to 3 and 5. Node 5 does not send the ball to children because it is observed, but node 3 is unobserved, so it bounces the ball to its children, nodes 2 and 6. Node 6 has no children, so the ball stops there, but node 2 is again observed, so it bounces the ball back to its parents, nodes 1 and 3. In turn, nodes 1 and node 3 both bounce it back to node 2. After this point, the ball may bounce indefinitely, but it has now visited all possible nodes. The final version of the Bayes-Ball algorithm maintains a list of nodes to be visited from parents and from children, and only visits the same arc in the same direction once to terminate the infinite loops that may occur in the simpler version of the algorithm. This is achieved by marking the nodes visited. Specifically, the algorithm marks the top of a node when the ball is sent to the node's parents, and it marks the bottom of the node when the ball is sent to the node's children. It also checks an observed node when it is visited. These marks not only allow the algorithm to terminate, but they also record significant results. For example, after running the algorithm, one will find that the irrelevant nodes are those that are not marked on the bottom. The requisite probability nodes are the nodes that are marked on top, and the requisite observation nodes are the nodes in K that are checked as visited. In the subsequent section, the proofs are given for theorems that state the Bayes-Ball algorithm correctly determines the irrelevant set and the requisite sets. It is also proved that the algorithm performs all this in time proportional to the node count plus the number of instant arcs marked during the algorithm. Therefore, the algorithm works in sublinear time to the size of the graph. The next section focuses on adapting the Bayes-Ball algorithm to determine the necessary information for decision problems represented by influence diagrams. Influence diagrams are belief networks augmented with decision nodes and value nodes. The decision nodes represent variables under the control of the decision maker, and the value nodes represent the criterion to be maximized. The uncertain variables are partitioned into sets such that some are observed before decisions and others are observed after specific decisions. The multiple value nodes in the influence diagram are related by a separable function, either a sum or product. The structure of the influence diagram assumes that the decision maker remembers all previous decisions and uncertain variables. And this is captured in the information sets for each decision. The requisite probability nodes are defined as the nodes for which conditional probability distributions might be needed, and the requisite observation nodes are defined as the nodes worth observing. Examples of the requisite sets from the Bayes-Ball algorithm are presented with an experiment decision model. The computational complexity of the Bayes-Ball algorithm for decision problems is also explored. It is shown that the sets of value nodes can be determined in linear time in the size of the graph. Additionally, the Bayes-Ball algorithm for each decision can be resumed, which keeps the previous results. The paper also demonstrates that the sets of nodes visited can grow monotonically as decisions are visited in reverse order. In conclusion, the strength of the paper lies in the rigorous mathematical description of all necessary concepts leading to the irrelevance and requisite information in belief networks and influence diagrams. The use of theorems and proofs convince the reader beyond doubt that the Bayes-Ball algorithm achieves its objectives within linear time complexity. Further demonstrations with example graphs help illustrate the steps in the algorithm clearly. The weakness may be the lack of a discussion on limitations or future research directions. The paper is closely related to the homework since this algorithm is introduced in class, and it is used to determine conditional independence in belief networks,